So to begin, let's talk about machine learning and profitability. As a quick primer for machine learning is training a model. And what we do is we put features into that model. Features are factors, they're measures or dimensions, and we'll train the model, and we'll test the model, and then we'll use that model to make predictions. There's two kinds of predictions we'll talk about. We can use regressions, and a regression is predicting a specific value, like how much profit, dollar value. And we can also talk about a multi-class classification. And in this case, we can group or bin into categories. So for example, unprofitable, below average, average, above average, whatever categories we want to set. And this is a good leveler for different practice areas or lines of business because we may want to normalize those bins to the practice area. So for example, if a practice area has a lower profitability margin than another practice area, if we're basing it on a percent of the standard profit for that practice area, then we can level set everybody. We can predict profitability at any level. We can look at it at the matter level. We can look at it at the work training level. We can even look at the task level. And we can see how profitable is this given task area. So let's talk a bit about the features. So at the matter level, direct costs, overhead costs, office, department, and team, client matter type, how we're leveraging our assignments, managing partner. We can look at write-offs and adjustments, and also discounts. Often in machine learning, you'll want to engineer your features. So we'll want to take, for example, our write-offs or adjustments and transform that into a percentage of overall billings, or rather than using the raw numbers, oftentimes we'll want to normalize to a standard scale. If we're doing certain kinds of regressions, then we'll want to do some normalization. So in the machine learning process, that's called feature engineering, where we take our features, our raw data, we transform it into the way that is most useful for our model. We can also do this at the work training level. We can use all the same features we used for the matter, but we could also look at by title, by dean year. We can look at the law school clerkships. The other interesting thing is look at a mentor program. So how does profitability, how is it impacted by how we've mentored, particularly our younger associates? And so whatever features we want to come up with, we can plug them into the model and build a model on this. And what we're going to talk about next is understanding that model and what features are most impacting that model. And that's really where a lot of this lecture is going to. But I wanted to just start out with a basic description of machine learning for those who aren't as familiar with it, what it means and how it works. Let's talk about the machine learning process. We have all the matters in our firm, everything historical, all the data we can get. We're going to break that into a training and a test set. We train typically on about 70% of our data, and we test that model on about 30% of our data. You only train on closed matters, matters where you know the answer, right? You can't train if you don't know the answer. But we go ahead and we build this model, and then we get a new matter that comes into the firm that we're budgeting. And we can push this new matter through our model, and we can predict the profitability. We've got matter one, we're going to stick it into our model, and it's going to predict our profitability one, and we predict we're going to get $150,000 profit from this matter. For example, if we're doing a regression and we're looking at actual dollar values. Similarly, matter two comes in, goes through the model, and the model spits out profitability of $260,000. So that's useful. We can look at that in a lot of different ways. But the question is, why? Explain the prediction. And this is where we start to move from machine learning model as a black box to a machine learning model as something that has to explain itself. Why did you make this decision? On what features did you base that value? We can then look at maximizing our profit by looking at how we optimize those specific features. This is an area called explainable artificial intelligence. It answers the questions of why did our model make a specific prediction? How much did each feature contribute to the result? Some features we can control. For example, work assignments. What attorneys are working and what work are they doing on this matter? Some features can't be controlled. For example, discounts or other things that have been negotiated and they're impacting the profitability. There's nothing we can really do about that at this point. And so what we want to do is we want to identify the controllable features that are having the greatest impact on profitability. So now let's get into game theory. This is fun, I think. We're going to talk about Shapley values. And the way Shapley values work, it's a solution concept in cooperative game theory. And the way it works is we have multiple players that have different skill sets that are all contributing to a venture that creates a collective payoff. what's the best way to divide the payoff? What's the fairest way based on the contribution? This is not unlike a law firm. You have a whole bunch of attorneys making different contributions to the firm. The firm has a profit, and then we distribute the profit to the partners. That's the problem that this game theory problem tries to approach. So in this case, we've got our 3 players, and they're contributing to some venture, whatever that happens to be. And they make unequal contributions. So the woman at the bottom is making the largest contribution. I've represented the amount of their contribution by the size of the arrow. The guy in the middle is the slacker. He's making the smallest contribution. And the woman at the top, the middle contribution. All of this leads to a payoff. This generates income. So the question is, who gets what? Of that payoff, how do we divide it? And there's very specific math around this. It's actually not very complicated math. And we can take this idea, people smarter than I have taken this idea and applied it to a machine learning model. And I'm going to show you what that means. So in machine learning, rather than players in a game, we have the features that are going into our model. For example, the leverage, which office, client discount. These are our features. All of these contribute to this model. The model makes a prediction. The question is, how much was each feature responsible for the prediction? So you can see the parallel between classic game theory and machine learning. And we can use this Shapley value analysis of our model to identify the features that have the greatest impact on our model. What can we do with that? If it's a controllable feature, we can look to optimize it. Okay? And when I talk about optimization, I'm talking about mathematical optimization, which is an area branch of mathematics. And optimization is a way of formulating a business problem and then finding the best solution to that problem. It's pretty easy to understand. We do this intuitively all the time. We have an objective, we have certain decisions that we can make, and we have certain constraints. So in this case, let's say, and I'm going to go into this in more detail in Excel, we have a matter. And the objective is to maximize the profit for that matter. Or it may be to minimize the cost of that matter for a fixed fee. Okay, those are different objectives, but they're both clear objectives. We have decisions that we can make. What attorneys do we assign to do what work? Those are the decisions. And then we have constraints. Well, an attorney can only work a certain number of hours a day. We can't just pick the cheapest attorney and assign all 1,500 hours to that person because they can't physically do the work. There are constraints on how much each attorney can work. There are constraints on which attorneys can do what type of work. So if we have a bunch of task codes, it may be that paralegals can work on 1 or 2 of them, but they can't do others. Associates of different grades could work on some. So we have constraints on who can do what kind of work. And then we also have the constraint of how much work is there. So those are our constraints. And the decisions we're going to make is, how do we staff this model? How do we staff this matter? Okay? And so this is a very solvable mathematical problem. There are lots of solver algorithms. There are linear algorithms, which don't exhaustively check all solutions, but they check a number of solutions, and they find the best solution in the space that they've checked, and they run faster. There are nonlinear solver algorithms that can be more exhaustive. So there are lots of implementations of this. I'm going to show you specifically an implementation that plugs into Excel. So I'm assuming many people in this room are Excel users. It's really easy to see how this works in Excel. It's a great plugin if you're not familiar with it. Excel has a basic solver plugin that comes with Excel, but it's not very good. And so there's a solver out there called Open Solver, which is open source, and much, much, much better. And I've got Open Solver plugged in, which is why I'm going to switch over to my machine when I do the actual demo. Now, doing a single matter, as I'm going to show you in a spreadsheet, is a great way of explaining how all this works. But if I wanted to push through hundreds of matters, it would be cumbersome in a spreadsheet. And so therefore, you would want to move programmatically into doing optimizations within Python or R or MATLAB or some mathematical programming language that gave you those capabilities. So before I switch over to the demo, in Excel, thinking that to just switch things over. Are there any questions on what I've talked about so far?
Is there a firm size or size of data set that's required before these models become accurate enough to be useful?
Yes. It's the problem of what we call overfitting. So if we have a small data set, the model may overfit to that data set, and then when different data comes in, it does not do well predicting on new data because it's overfit to the old data. So that can be a problem of having a small data set. It can be a problem of having a not well-chosen data set. If your data set, when you do that 70-30 split, you have to make sure that all cases are represented. So how much data you need to have and how valid your predictions are, there's lots of ways of going about it. So one thing that can be used is called cross-validation, where you'll take a data set and you'll break it into a number of pieces, and you'll train on each one successively and then merge the results. You can always look at, as long as you have a holdout set, a set to test on, you can always look at how accurate are my predictions. And if you're not reaching your target, then the model's not good.
And in your experience, what is that data set size? Is there a firm size? Once you hit so many lawyers, you're probably big enough to make this work, or once you have 3 years of data or 2 years of data, it's probably big enough. What are those parameters?
It's hard to say without how much variability there is in the data, how much noise there is in the data. But I would say, so I have the luxury of being from a fairly large firm with 20 plus years of data. Now you also have to think about the way matters were managed and billed and collected on 10 years ago may not affect the way they are today. So you have to, once again, be careful with your data sets. But excuse me, I think having a probably 2 or 3 years of data for a medium-sized firm is probably sufficient. Once you get into the the nitty-gritty of it, you can see whether your predictions are holding up or not. Anything else sort of generally?
Seems like this approach would work best with medium to large litigation matters, medium to large transactional matters. Does it work well on general counsel type work or regulatory type work where the staffing doesn't have a traditional shape?
Yeah, so it's a good question. And I like the description of a law firm being, a conglomerate with a lot of different lines of business, right? So I think one of the most important things is to break your models out by practice area. I think the other thing that's interesting about machine learning is that you don't want to go in with too many preconceptions about what's going to impact the model. What you start to do is look statistically at correlations. You can do Pearson correlations and other kinds of calculations to see what's going on, but oftentimes the data surprises you. There's also the degree of variability in your result, right? So if you are, one practice area has got profitability numbers that are in a fairly thin band, then you have to ask yourself, what am I predicting? Should I split those into 2 bins? Should I split them into 3 bins? So the data really has to lead you in each case, and I think you do have to look at practice areas independently. Although the great thing I think about machine learning modeling is that you can run it lots of ways. You can run the model firm-wide, you can run the model for a given office, you can run the model with one set of features, you can run the model with another set of features, and you're getting good statistics back about what is correlating, what's not correlating. And so there's absolutely no magic bullet here. A lot of people, I'll get you 1 second, a lot of people think that with machine learning you plug all the data in and it magically gives you an answer, and it's not even remotely like that. It takes a lot of work. You have to question your results, you have to work with the people who really understand it, and you have to constantly be questioning and fine-tuning your models.
I'm pretty sure I have no idea what you're talking about. Everybody else.
Sorry. I have not done my job.
So a matter comes in, you predict what the profit's going to be. Number one, how often is that accurate? Within 5% of accurate, or whatever percent you accept. And why does it matter, as opposed to assessing what the profitability was after it was completed?
Yeah, so it's a good question. Prediction is one use of the model, right? And so we can say that we are predicting a regression value, an actual profit number within a certain percentage of accuracy. We may decide whether that's good enough or not. Now, will that comes from our test set, right? So we train, we test, we get our accuracy. then we get new matters coming in the firm. We predict based on that model, but we won't know until that matter has closed whether that prediction was accurate. So you've got to constantly, there's care and feeding of the model, right? So the model gains trust over time. Predicting is useful in some regards. I think there's other ways of doing forecasting and other other of those types of analyses. What I'm getting at though is building the model, but not just using it for predicting, but using the model and understanding the model to figure out which are the knobs and levers that I can turn to maximize my profitability. What's having the greatest impact? And then look and see, is that a controllable feature? And if so, then it's a management question. How do I improve that number? Machine learning is fun for me because it's art and science. There's hard numbers, there's hard processes, but there's a lot of, why isn't that working? And maybe we should try this. And there's a lot of integrating it back into the real world. All right, let me switch time-wise. I got 10 minutes. Let me switch over. I'm going to go through this example here. This is just a quick spreadsheet with some made-up, although reasonable, numbers for which attorneys have worked on which tasks and their title, and how many hours, and their rate, and their cost rate. Okay, so this is like a basic, I've got a matter, I know who worked on it, I know how much they worked on it, I know what we charged for them, I know what their cost was. First step is I'm going to go pivot this and just do a quick pivot of this data. And when I pivot the data, I've got my timekeepers down the left, and I've got for each task code, so C100, 200, 300, these are task codes, I've got the sum of their work hours, their average work rate, all of that. So I know which attorneys, how many hours per task they're doing. And if I scroll all the way over here, I've got some sums on the right where I've got their total number of work hours, their average work rate, their average cost rate. And then at the bottom here, I've got my calculations of total cost for this matter, the total billed for this matter, and the profit for this matter. Now, I'm going to bring this into OpenSolver. I'm going to show you how this works. I've got the same pivoted spreadsheet, but now I'm in Solver. And so what I've done is I've just had our decision space, which is the number of work hours each attorney is going to work on. Now, what OpenSolver does when you show the model is that everything that's a decision space is pink. Now, I've got all my associates up top, and associates can work on any task code. And I pulled that from the fact that associates worked on all task codes. But as I come down here into the model, I've got a timekeeper type of C1, or L for paralegal. And they only did work on certain task codes. So I'm going to say they can only work on those task codes. So these are decision spaces, these are not. I can't fill in these values. I can only use, everyone can only be assigned to a task that somebody in the real world in that title actually worked on.
So you're highlighting these pink?
I did. So when I went into my model in OpenSolver and I built my model, I said, these are my decision cells. These are the ones you can change, and I had to go in and specify them, yes. And this is where it can become a bit cumbersome working in OpenSolver as opposed to working programmatically. But I wanted to be able to demonstrate everything. Now I have constraints here. The constraints are that these columns are tasks. These are the actual number of hours that were performed on this task. So no matter how I redistribute them, I still have to do the same number of hours because the tasks are the tasks. Now, granted, one attorney might have done it faster than another. There's always, you have to make assumptions in a model. There's a great quote, I think it was George Box, a statistician, who said, all models are wrong, some models are useful, right? And that's where we are here. We're taking reality, we're making assumptions, we're going to build a model, and hopefully it's going to be useful. The other constraints that we have are, on the right, I am going to say there is a maximum number of hours that each attorney can work on. So once again, I can't assign it all to the cheapest guy, right? And what I did to calculate that is I have a factor of 3. I took their average hours, I took their actual hours and said everyone could work 3 times more than they did before. And it's actually kind of fun to play around with that. But in an actual budget, you could go down and say how many hours you expect each person to work. You could fill those in manually. What I'm predicting is profit. And so profit down below, I'm predicting it, and I am trying to maximize it. When I solve this, I just click Solver, now it's going through, and it's a linear algorithm. That was like 2 seconds, and it tried a whole bunch of possibilities and optimized the values. So here, it came up with 1,040,000 as a profit, and if we go back to our pivot, we actually got $763,000. So we picked up $240,000 on this matter. Now let me show you, let's say this is a fixed fee matter. I'm going to go back to Timekeeper Solver. Now I'm going to show you a little bit behind the curtain here. I'm going to open up the model design screen. So this is where I built my model, and this is where I can choose my engine, et cetera, et cetera. What I'm going to do is I'm just going to change, up top I've got my objective. And right now my objective is to maximize cell 92, which is profit. I'm going to change this to minimize cell 90, which is my cost. So now, rather than maximizing profit, I'm going to minimize cost. And right now the cost is $2.8 million. So if I go ahead and solve, Solver's now going to have a different target. It brought the cost down to $1.2 million. It shaved $1.6 million off the cost of this matter, just by pushing around attorney assignments. So if this was a fixed fee matter, and I'm getting the same dollars for it, I'm going to minimize excuse me, my cost. If it's not a fixed fee matter, I'm going to maximize my profitability. And that is just by mathematically trying various possibilities. The algorithms are fascinating for anyone who's really geeky and wants to dive into them. There are lots of different ones, but it will, within a couple seconds, show me how I can take this matter. So you have a matter budgeting process, and you say they're going to be this many hours in these task codes, and these are the attorneys that can work on them. You can actually plug it into a model like this and optimize the assignments. Now, granted, real world is a little different than what gets spit out the model. This person, you have to work around actually assignments, but you can actually look at a range of costs or profitability. That in the word, I could go ahead and minimize profitability just for fun and maximize profitability, and that will show me what the range is for my, for this matter. What could I make on this matter from low to high? So that's it. Thank you very much.
Thank you.